Hello, welcome back to another one. We're going to be solving some more thermodynamics problems today. This one is also from Reif. Specifically, it's from, I believe it's 515 in Reif. And this problem covers a unique little setup in which we have a filament and some barrier that is moving or has some force being exerted onto it. In particular, the problem itself reads, oh my goodness, that we have a soap film, which is the shaded area of our diagram up there, is supported by a thin wire frame, right? So there's some surface tension that is being exerted on the wire, and that surface tension is given by the value of 2 sigma L, right? So this particular wire tends to move in a direction such that the value x, which I have in a bracket there, also tends to decrease the size of the soap film, right? We also know that we can rewrite sigma as being a constant sigma or sigma naught minus alpha times the temperature T, where sigma and alpha are both just some arbitrary constants that are independent of temperature or the position x, right? So we're asked to find 3 things in particular, and those 3 things in particular is a relationship for a change in energy, or the change of mean energy, dE, in the film, in terms of the change of heat absorbed by it and the work done by some infinitesimal quasi-static process by which we change x some amount dx plus x. Secondly, we are asked to find the change in the mean energy, delta E, right, which we can write as being an expression of E minus E naught, or E0, my bad. And then last but not least, we need to find the work done on the film to stretch it at a constant temperature from 0 to that distance x, right? So for our first component of our problem, I'm going to shuffle over to the other side here, right? So for our first part of the problem, we're going to look back at some stuff from chapter 2, namely our generalized force conjugates. X sub A of R is equal to a negative change of energy by that change in some parameter d of x, right, sub alpha. Now if we have some generalized force, we can say that F is equal to the negative change in energy times or divided by that change in distance dx. Do some substitution, or not substitution, some separation of variables, and then we can just simply write our change in energy as being a value of negative sigma, 2 sigma, times the length times that infinitesimal change of position d of x. Now we know an equation for our inexact differential dq for heat. We know that that's equal to the temperature times the change in entropy, and we know that the temperature times the change of entropy is equal to the sum of the change of the energy plus that of the volume, or change in the volume plus the pressure, right? I'm sorry, let me rephrase that. The change in energy plus the pressure times the change in volume. My goodness, these are long sentences. So we know that this term is equal to the work, and then we know that f dx, or negative f dx, is equal to the change in work. So we just plug that into our solution, and then we can get our expression for E, or change in energy, in terms of our inexact differential and the surface tension term, right? Now this is where it gets a little bit more mathematically tedious. As you can tell, I kind of began to run out of space, but I'll pick up here and then I can finish the problem once I'm done explaining it. I'll erase everything and finish writing stuff down, right? So in order to get our change in mean of energy, we have to take a lot of different steps. And Reif, in his solution manual, he starts off with entropy. So I decided to kind of follow my nose with that regard to see how he finished this problem to get an expression for delta E by starting off with entropy. So we start off with the differential definition of entropy, in which we have partial derivatives of entropy with respect to its parameters x and t, right? we already know from up here what d of E is equal to, right? So we can actually either choose to rewrite it, or we can go this route, which is what Reif does. I'm sorry, that's not rewriting it. I don't know why I said that. We get from the TDS equation up here what our change of energy ought to be, or rather from right here, what our change in energy ought to be, and then we can substitute that in for our change in entropy. And then what we do is that we take this differential, because we don't want this in terms of change in energy, we need it in terms of changes in position and changes in temperature. So we take its differential definition, we make energy a function of position and a function of temperature, and then we plug that back in to our equation for entropy here, right? So we get this long, ugly expression where we have 1 over the temperature times the change of energy with respect to position plus the change of energy with respect to temperature minus our force divided by the temperature. Then what we can do is that we can group these in like terms with respect to their incremental changes, or the respective incremental changes. So our surface tension and our derivative with respect to E with respect to X, those are all changes with respect to X. So we group them together, and then we have just part E, part T by itself over here in that column, right? So from direct comparison with the differential definition of D of S, and then the explicit definition of D of S, we can concretely say that the change of entropy with respect to X is equal to this term here, where we have the differential of E with respect to X minus the surface tension there. Now the issue here now becomes that we have some concrete parameters that we know we can actually measure with energy, sigma, length, so on and so forth, temperature, you know, and then we have something that isn't necessarily measurable. It's a calculated variable in entropy, right? And because it's a calculated variable in entropy, we need to find a way to re-express this so that we can have something to compare it to and substitute back in, so we can finally get something for E, or rather even for just for entropy. So what we do is that we pick on some of our Maxwell relations, and one of our Maxwell relations that has all of the particular variables that we're looking at, namely energy, temperature, and entropy, is our Helmholtz free energy. And our Helmholtz free energy, F, is written as energy minus the temperature times the entropy, right? So we take our differentials, and we get that we get dF is equal to dE minus S dt minus TdS, because when you take the differential, you apply the product rule in TS there. And then when we substitute this variable for dE from up here down into our expression for our Helmholtz free energy, our TdS terms cancel out, and we're left with just 2 sigma LdX minus S dt. So that's what we have down here. Now we can also look once again at our differential definition of the Helmholtz free energy, which we get in terms of d of f times, or by d of x plus d of f d of t, right? So once again, by direct juxtaposition of our two expressions, once again, we see that the partial of our Helmholtz free energy with respect to x is equal to the surface tension term, and our partial derivative of the Helmholtz free energy with respect to temperature is equal to negative entropy. So now we need to use something called the method of exact differentials. And if you've had a partial differential equation class or just a regular differential equation class, you might remember this. And basically, it states that we can have two particular variables m and n, and they can, or rather a differential equation is considered exact, or two differential equations are exact, if the partial derivative with one of them with respect to one variable is equal to the partial differential of the other one with respect to another variable. So in this case, if we allow y in this expression be equal to our temperature, and x, just let it be equal to x, then we'll see that our value for m is equal to negative entropy, and our value for n is equal to the surface tension. So we can write that our partial derivative of entropy with respect to x is actually equal to negative 2L sigma, or rather just negative 2L times the derivative with respect to sigma, the derivative of sigma with respect to t. Wow, that was taking a lot out of me for some reason. So with this in mind, what we can do is that we could take this and plug it back in for our expression of entropy, or change in entropy with respect to distance x. Okay, so now that we have our expression for our partial of entropy with respect to position x, what we can do is that we can just substitute our value for sigma and take the derivative. So that's what we do up here, right? So we take our derivative with respect to temperature of sigma, and we get that our partial with respect to, of entropy with respect to position x is equal to 2 times L times alpha, right? So now that we know that, we can finally take our expression, which has our change of energy in terms of x, and reorganize it such that we are writing this change in energy in terms of everything else. And when we do that, we get this expression here, where you have a change in energy with respect to change in x is equal to 2 times sigma naught minus alpha t. It's not really well written, but that says minus alpha t, right? Times change in length. All I did was substitute alpha in for here for sigma, plus 2 times alpha t times L. I'm guessing L is length, I don't know. It's just some number. So we substitute it, I'm going to substitute that in. We FOIL our 2 and our L across both of these terms. We note that these two guys cancel. So all we're left with is 2 sigma naught L. And we just do some more separation of variables, and we assume that our partial of x is equal to some greater change of x, or we say that it is. And we get that delta E is equal to 2 times sigma naught times L times delta x. This allows us to treat energy strictly as a function of x. So when we plug in x equal to x and then subtract from it x equals 0, we're just left with 2 sigma naught L of x. And that is our expression for our average energy, or a change in our average energy, right? Now, part C is much more simple. As you can tell, I did it in, 4 lines? Yeah, and even then it was just a matter of substituting. You could do that in your head if you wanted to, but all you do is that we know that the work done on something is equal to the negative of the force being applied times some change in distance, right? So when we do that, what we do is we just integrate both sides from 0 to x, and we get negative 2L sigma x. Now what's really interesting about this is that we can notice that our work is actually just simply the negative of our energy, except they differ by some constant sigma naught, or rather this one is sigma naught known as constant of sigma, but then they would really only differ by an amount alpha times t. But we could probably relate this back to our first law and find out, maybe what our heat is from that kind of expression, play around with it a little bit further if we wanted to extend it. But yeah, basically what we did with this was that we explored how we can use our Maxwell relations in terms of equations that otherwise might not be too terribly obvious, and we exploited the definitions of our partial differentials and our differential equations to solve a system of equations with a bunch of unknowns in it. And then we also use our principle of exact differentials, right, to try and reparameterize what our delta, our change in entropy with respect to position x would be. So a lot of different skills being used here. Most of it is just knowing separation of variables and knowing algebra. But nonetheless, it can be pretty tedious to get. It can be pretty tedious, and it can be very easy to get lost in the numbers. But yeah, thank you for watching. Let me know what y'all think.